Ever wondered how a chunk of industrial metal becomes a flawless coin worth holding in your hand? The truth is, it doesn't start shiny. It starts messy, hot, and rejected over and over until only perfection survives. Today, we're pulling back the curtain on something most people never think about: the brutal, precise, almost obsessive process that turns raw, precious metal into the coins investors actually trust. And here's what makes this relevant right now. With precious metals getting more attention and bars and coins taking bigger market share versus jewelry, mints are under pressure to produce more, while counterfeiters are getting creative. So understanding how real coins are made isn't just interesting, it's actually protective knowledge. What you're about to see is the complete journey from formless metal to finished product, told in 2 layers. The physical reality of what actually happens on the factory floor, and the why behind every step. Because in this process, nothing is accidental and every detail exists for a reason. Before there's anything resembling a coin, there's a decision that happens in facilities that look more like industrial kitchens than treasure vaults. Refined precious metal arrives, but it's not in a form that machines can work with efficiently. What production floors need are logs, billets, strips, and coils, shapes that can be rolled, sliced, punched, and fed through equipment without cracking or drifting out of specification. This first transformation is simple in concept, but brutal in execution. You take refined metal, melt it down, and reshape it into something usable. And usable doesn't mean pretty, it means predictable. Silver typically gets factory line treatment, while gold and platinum receive the surgical gloves approach, and that difference shows up immediately in how facilities handle each metal. For silver, you can take large batches of refined bars, cut them down, and feed them into melting and casting operations that produce big, solid logs of metal, intermediate pieces designed to be processed rather than admired. These logs are stable, they cool into consistent shapes, and they can be cut into chunks that get heated and pushed into forming equipment without the metal behaving unpredictably. Gold operations feel slower and more controlled because with gold, a tiny mistake isn't just a defect, it's an expensive defect that can't be casually absorbed. Sometimes the process involves creating alloys, mixing pure gold with other metals to create coins that are tougher and more scratch-resistant. And alloying stations are kept separate from pure runs because when you're dealing with purity standards, cross-contamination isn't a risk you take lightly. It's a disaster waiting to happen. The entire building becomes a machine designed to hit exact targets, and facilities with institutional reputations have earned them through decades of hitting those targets consistently. What matters here is understanding that purity isn't a personality trait, it's a parameter, and the manufacturing process is built around delivering that parameter every single time. Once you have cast bars and logs, the real physical work begins, and it starts with a problem that sounds simple but requires careful engineering to solve. Metal doesn't want to change shape, and when you roll it thinner, you're literally rearranging its internal structure in ways that cause it to harden and resist further work. This isn't a metaphor, it's metallurgy, and the moment a thick cast bar starts getting rolled into a strip, it begins fighting back. If you try to force the issue with brute strength, you lose because you get cracks, stress lines, and strips that look acceptable until they're punched into blanks, and suddenly weights are drifting and edges are misbehaving in ways that ruin entire batches. The solution is annealing, a controlled heating and cooling process that softens worked metal and makes it workable again so it can continue being rolled and shaped without breaking. This step sounds like a footnote in most descriptions, but it's actually a main character in the story because without annealing, the entire process would grind to a halt. Modern annealing often happens in controlled environments designed to reduce oxidation so the surface doesn't come out looking aged and damaged, because surface quality established early in the process determines how much correction work you'll need later. Standing near industrial annealing ovens gives you immediate respect for the people doing precision work in environments that are actively trying to cook them, because the heat is that intense and that constant. While gold moves through rolling mills and annealing cycles in measured batches, silver often takes a different route entirely, because silver loves volume, and the question with silver isn't whether you can make it, it's whether you can make enough of it. Silver coins are produced in enormous quantities, and silver demand isn't just collectors and investors, it's industrial applications like electronics and solar that quietly consume silver in the background of modern technological life. On production floors, silver gets pushed towards speed and automation, with thick billets heated until they're ready to move and then subjected to heavy mechanical force that forms them into long strips, wound onto coils that look like giant rolls of ribbon, but move like objects that could crush your foot because they're heavy, awkward, and require specialized equipment just for transportation around the facility. Even after you have a coil, the work isn't finished because close isn't a specification, and coins have very tight tolerances where thickness is one of the critical measurements. Coils get run through gauging operations, essentially controlled rolling where thickness is measured and adjusted continuously until the strip hits its target. Modern technology makes a massive difference here because laser-based measurement systems can monitor thickness in real time and help maintain consistent output, which dramatically reduces the number of blanks that come out too heavy or too light. Older methods relied far more on manual measurement and manual adjustment, and you can imagine how that story ends with variation, inconsistency, and higher reject piles that cost time and money. There's a common assumption that manual processes mean higher quality, and sometimes that's true, but in thickness control, automation can actually protect quality because it removes human fatigue, reduces guesswork, and maintains tighter tolerances over long production runs. The best system isn't manual or automated by ideology, it's whichever system delivers control without introducing new failure points. Once the strip is dialed in, something else happens that most people never notice. The strip has to be straightened because coils are convenient for storage and handling, but they're not naturally flat. Before blanking can happen, many mints run coils through equipment that straightens the metal and feeds it cleanly into blanking presses, and this is where the workflow starts feeling like a magic trick, because you put in a long ribbon of metal and out come perfect little discs that are the before picture of every coin. Blanking is exactly what it sounds like. You punch discs out of the strip like a cookie cutter, except the cookie is made of precious metal and the cutter costs more than a car, and the precision required is extraordinary because dimensional consistency at this stage determines success or failure later in the process. One detail that adds important context is that not every mint makes every blank. And even major facilities sometimes buy blanks instead of making them all in-house because blank production is its own specialized industry requiring dedicated presses, quality systems, and constant battle against tiny dimensional drift. When a mint does produce blanks internally, what you're seeing is vertical integration, a facility that controls more of its pipeline and can respond faster when supply chains tighten or demand spikes while others wait on plancher deliveries. Blanking creates two things simultaneously. It creates blanks and it creates scrap. And that leftover strip, the webbing and donut-shaped remains, goes right back into the melt stream. This is why mints can operate at scale without wasting metal the way people imagine, because the process is designed like a loop where metal becomes strip, strip becomes blanks, and scrap becomes metal again. Depending on the metal and product, blanking can look very different, with silver often heavily automated, while gold and platinum operations slow down and become more hands-on with smaller batches, more careful handling, and operators physically feeding material and collecting blanks, because the priority shifts from speed to surface integrity and defect control. The practical reason is simple. The more valuable the blank, the less you want it flying around at high speed. You want it controlled, tracked, and handled like an object rather than like confetti being scattered. If you're thinking that having blanks means you're ready to strike coins, you're wrong. Because a blank isn't just a disc, it's a promise that the finished coin will hit the exact weight range it's supposed to hit. And this is where the process becomes ruthless in its standards. Every blank gets weighed. And this isn't a sampling process, it's literally every single blank going through weight verification, and this is where robotics make total sense because robots don't get bored, distracted, or decide to eyeball measurements. If a blank comes in underweight, it can't magically gain metal, so it goes back to melt, and if a blank is overweight, you have a different problem because you could strike it as is, but then you're giving away extra precious metal in every coin. And over a large production run that's not a rounding error, that's a serious amount of value walking out the door. Overweight blanks go through an acid-based correction step called pickling, where a controlled process dissolves away tiny amounts of metal until the blank falls into the acceptable weight range. When people hear acid bath, their brains go straight to horror movies, but in coin production, this is a normal industrial step used for cleaning and fine-tuning, and official production descriptions from various mints discuss pickling and burnishing as standard treatment steps for blanks, especially when higher quality finishes are required. The system isn't random either. Blanks are often grouped into weight categories because a blank that's barely heavy needs less correction than one that's significantly overweight. So you don't throw everything into the same bath and hope for the best. You control exposure, timing, and outcomes. What people miss about pickling is that it's not just about saving metal. It's about compliance because coins, especially legal tender bullion coins, are manufactured to specifications for weight and dimensions that matter for trust, for trading, and for the entire reputation of the program. That's why product pages spell out purity and weight parameters in almost legalistic language, because the coin isn't just pretty, it's a standardized unit that needs to be defendable. There's another layer that's become increasingly important, and that's counterfeits, because as coin demand rises, so does the incentive for fake products, and modern bullion coins increasingly include authentication features that are hard to replicate, sometimes even micro-engraved details that require magnification to see properly. After pickling, blanks can come out with a duller, almost frosted appearance that surprises people who've only seen finished coins, but it makes sense when you realize you're looking at a surface that's been chemically cleaned and prepared. This is where burnishing enters the process, and burnishing is the pre-strike polishing and cleaning phase that makes blanks look uniform, removes tiny surface marks, and helps the blank take a strike cleanly. The process often involves rotating drums, specialized soap, and stainless steel media that tumbles and gently polishes the blanks over extended periods. And here's where the timeline surprises people, because this isn't a quick rinse. It can run for hours, with 2 hours being normal, and some batches pushing longer because surface perfection is non-negotiable. Burnishing accomplishes something else that sounds trivial until you've seen the damage it prevents. It helps avoid water spots and surface roughness that can appear later if the blank is struck before it's properly conditioned. Older technical documentation on planche preparation describes burnishing and drying specifically as methods to smooth surfaces after annealing and cleaning, so the final strike has a better chance of looking finished instead of patchy or inconsistent. There's another step that sounds small but changes everything, and that's the rim. Before striking, many blanks go through an upsetting process that forms a slight raised rim around the edge, and that rim matters enormously because it protects the design, helps metal flow correctly during striking, and transforms the blank from a flat washer into a coin-ready shape. Some older public descriptions of coin production describe blanks being annealed, cleaned in acid, washed and burnished, and then passed through machinery that corrects shape and forms that characteristic rim you see on most coins. By the time a blank is headed to the press, it's not just clean, it's sculpted in advance. And every tiny preparation step is basically insurance, because the press is about to slam a design into it with enormous force, and any weakness or flaw will be exposed immediately. Imagine you're a blank that's been melted, cast, rolled, annealed, gauged, straightened, punched, weighed, pickled, burnished, and rimmed, and you're still not a coin, you're just finally worthy of entering the press room. The press room is where everything done so far either pays off or gets exposed because the press doesn't forgive anything. If there's debris on a die, you'll see it on the coin. If there's dust on a blank, you'll see it on the coin. And if the collar isn't positioned correctly, the edge will tell on you. Before striking, operators clean obsessively, wiping down and inspecting dies, using compressed air, and double-checking surfaces. And yes, it can look almost neurotic, but there's a reason for the obsession. The press is basically a truth machine that takes whatever is on that blank and stamps it into permanent history, and once the design is there, you can't unsee a defect. For high-volume silver coin production, presses can move fast, approaching 10,000 coins per hour when everything is dialed in and the setup is optimized for speed, and that speed is exactly why all the upstream steps matter so much, because when you're striking that quickly, you can't afford a steady stream of bad blanks. You need blanks that are already disciplined and ready. The collar deserves special attention because it's one of the most underappreciated parts of coin making. It's the ring that holds the blank during striking, helps define the outer edge, can create reading or lettering, and keeps metal from flowing outward in ways that would distort the design. The collar is simultaneously part of security and part of aesthetics, and when you look at a coin edge and think it feels intentional, you're right. That's engineering doing its job. Dies wear out and don't last forever because every strike is stress and friction. And the deeper the relief in the design, the more work the die is doing. So mints invest heavily in die making, die maintenance, and die handling, because a damaged die doesn't just ruin one coin, it can ruin an entire run before someone catches the problem. When a coin comes out of the press, it's tempting to think that's the finish line. But it's not, because after striking comes quality control, where dreams go to die. A lot of people imagine quality control as one person with a lamp squinting at coins and making thumbs up or thumbs down calls. And that does happen, but on higher volume lines, you'll also see automated sorting and camera-based inspection doing first pass work, because when coins are coming out fast, you need systems that can keep up without letting mistakes slip through. Automation catches obvious problems like misstrikes, incomplete fills, edge problems, and major marks. But collector problems are sneakier, like a tiny line that only shows at certain angles, a small spot that appears after handling, or a faint haze visible under harsh light. Those are the defects that make final human inspection so important, especially for premium finishes where buyers expect perfection rather than pretty good. So quality control becomes a layered defense rather than a single gate. A tiny mark, a subtle line, a small surface flaw you'd never notice unless someone pointed it out. Those can be enough to reject a coin because the rule in high standard mints is simple. If it's not perfect, it doesn't move forward. Rejected coins get melted and recycled or potentially downgraded for different channels, but they're not supposed to end up in the same pool as perfect coins because the whole point is separation and maintaining standards. Ultra-high relief coins represent one of the weirdest and coolest subplots in manufacturing because these coins have designs that rise dramatically, almost like sculptures. And that relief is what makes them attractive. But it's also what makes them nightmares to manufacture, because when you push metal into extreme relief, you're asking a lot from the die, from alignment, and from pressure. If you try to do it in one normal strike, you run into problems like stress on tooling, cracking risk. imperfect fills, and misalignment. So one method for extreme relief involves striking an oversized piece first, creating the relief with extra margin, and then trimming away the outer ring so the final coin is smaller, cleaner, and more controlled. Some people think that sounds wasteful, but in mint environments, that outer ring is still precious metal and inventory that goes back into the loop, and if trimming reduces die failures and bad strikes, it might actually be more efficient overall, even if it looks dramatic on camera. After all that, there's still finishing, and finishing is where a coin becomes a product, with some coins struck, inspected, and basically done, while others go through additional cleaning steps to remove residues from handling or striking before being dried and prepared for packaging. Proof coins look different because they receive extra blank preparation, extra handling discipline, and sometimes multiple strikes, because the goal isn't just make a coin, the goal is make a coin that looks like a mirror and stays that way. So that's the complete story. Metal arrives refined, gets melted and cast into workable forms, gets rolled and softened repeatedly until thickness is controlled, gets straightened and punched into blanks, while scrap loops back into the system. Every blank gets weighed with out-of-range pieces corrected or recycled. Blanks get cleaned, pickled, burnished, and rimmed before ever seeing a press. Dies and blanks get cleaned like lives depend on it. The press strikes the design while the collar shapes the edge. Quality control filters out anything that isn't perfect. Special products use special methods like oversized strikes and trimming for extreme relief. And finishing turns the raw strike into the coin you actually want to hold. The next time you see a coin online and wonder why it's priced the way it is, remember, you're not paying for a circle of metal. You're paying for the process that makes that circle trustworthy. What surprised you most about this process? Was it the individual weighing of every blank? The use of acid as a precision tool? Or the fact that the shiny coin moment is actually the result of hours of unglamorous preparation? Drop your thoughts in the comments because I always learn something from what you all notice. And if you're doing well with your investments or collection, share your success story so others can stay motivated, because seeing real wins from real people helps them stick with their own strategies. If you want me to go deeper on the security side, the collars, the reading, and the anti-counterfeit details hiding in plain sight, let me know in the comments and we'll do a full breakdown next. Thanks for being here. Take care of yourselves and each other. And remember, this is educational content based on publicly available information and general industry practice, not financial advice. So make your decisions carefully and do your own homework.